So the next speaker is Stjepan. I can call him my friend and a good colleague. And just as a side note, Stjepan is not only one of the all rising stars in cybersecurity, and specifically how he is recently using machine learning for side channel attacks. Very exciting research, actually. Stjepan is also a long-term Wing Chun fighter. So that means he knows the art of Kung Fu. So be very gentle when you ask questions. No, Stjepan does really amazing work, and this is why I always want to invite him. Very refreshing work, very, I would say, cutting-edge research, and he's going to give this talk on, so to say, reverse engineering of neural network architectures through side channel information, which is actually one of the recent research direction, which will surprise you what people can find out amongst others, Stjepan on in his research. So Stjepan, the stage is yours.
Thank you very much, Ahmad, for a very nice introduction. I'm not really serious. Yeah, do ask questions whenever you want, please. Don't listen to Ahmad. Let me share my screen. Hop. Okay, can you see the screen?
Yes.
Cool. So, yeah, I will talk about a topic we did some time ago. It's reverse engineering neural networks architectures through side channel information. And let me give you a quick overview of what the talk will consist. So it's basically 3 parts. I will first give you introduction. Why do we do attack like this? Why do we care about something like that? And then I'm go into details how to reverse engineer neural networks. And I must add, it will not be only the architecture, it will be also the model, so the parameters of the model. And then finally, I will also give you a very quick overview, how can we combine that attack, a different type of attack, so that we also, at some point, we can recover the input of neural networks. In that way, we kind of build a system to first recover the architecture, the model, and then after that, to use the knowledge of the architecture, the knowledge of the model to also obtain future inputs. So, in essence, we all know, I mean, machine learning is a buzzword. It's something that many papers, many people use as a technique, as a strong tool to make the research stronger. But it is also a word that many of us sometimes use because it makes more sense for various setups to evaluate, because it allows us to assume less. If you compare with simpler machine learning techniques, we need to do pre-processing, we need to do feature engineering, but then we go to deep learning, stronger models, and then somehow we are left on an easier position. And this is what we see in the last number of years. So many applications, but also security applications. And when we talk about that, what we need to realize is, especially from the company perspective, is that developing a strong machine learning, deep learning model is an asset. And many companies actually do invest a significant amount of time and money to develop. So spending hundreds of hours of designers, spending huge amount of computational power, this costs money. And in the end, the question is, if there was the effort to develop something and the company or whoever wants to keep it private, how difficult it is for some attacker to reverse engineer the architecture, to reverse engineer the model. And of course, this is nothing novel as a question, because people investigated leakage of sensitive information about individual data records, and reverse engineering works, for instance, on CNNs, where researchers use timing, they use memory leakage, they exploited line buffer in convolutional layer of CNN. But commonly, those works assumed something specific, the model was implemented on exactly this, and because of exactly that, we can reverse engineer. What I want to talk is, can we go a bit more general? Can we assume less? How do we implement? Of course, still some assumptions will need to hold. And then, can we still reverse engineer efficiently, successfully, everything we want to know about deep neural networks? So here I will talk about multilayer perceptrons and convolutional neural networks as two, let's say, relatively common examples in many domains, and the same type of the attack can be used also for other types of networks. So what is important to mention about these two types of neural networks is that they consist of different types of layers. So our multi-layer perceptron, every layer will be dense or fully connected layer. Our convolutional neural networks commonly consists of three types of layers. So convolution layer, pooling layer, and fully connected. And combinations of those layers or some of those layers are also commonly seen in different architectures. So that being said, let's immediately see how can we reverse engineer a neural network by using side channel information. We will make no assumption on the input or the source. Thus, for us, it will mean we will work with real numbers, so floating point values. Why? Because whatever kind of input you think of, you can represent with those kinds of values. And one very important assumption we make is that we assume the machine learning algorithm will not include any side channel countermeasure. And now I know this can sound like, oh wow, but this is a huge assumption. Why do you say something like that? But unfortunately, it is still reality, because when we are talking about practical deployment of deep learning models, those models will not have countermeasures against side channel attacks. Why? There are multiple reasons. One reason could be people are still not convinced enough about the attacks, that this is reality, that this is a proper threat. Second, even at the moment when they are convinced about the threat of side channel attacks for reverse engineering neural networks, common countermeasures that one could think of, something borrowing from crypto, they come with a cost. And then the big question is, do we want to impose that implementation costs, so either bigger area or bigger power consumption or slower speed, do we want to impose it on something as sensitive, as already computationally heavy as deep learning? Think just of the examples of self-driving cars. The batteries on those cars can be quite quickly exhausted because of the complexity of normal calculations they need to do with neural networks. And now think of it, if the battery would last only half the time because you added countermeasures. Of course, you could say we are more secure, but the usability reduces significantly. So let's talk about the attacker. What do we want to do? We will consider a common side channel attacker, so passive one, someone who just observes. We will acquire measurements, the device that works in a normal setup, and we will not interfere with internal operations by evoking faulty computations. That being said, if you are interested in that kind of direction, there are multiple works where people do fault injection to inject a fault in your neural network to make reverse engineering attack or some kind of attack. Next, we will assume that the attacker does not know the architecture of the network, but can feed random, so known inputs to the architecture. Okay, and attacker is capable of measuring side channel information leaked from the implementation of the targeted architecture. The targets I mentioned here are small embedded devices, something that would be used in IoT setups. So think of sensors, think of actuators, so Atmel, Atmega, and ARM Cortex. Of course, this does not mean you cannot also do attack on more serious devices, so FPGAs, GPUs, and there are recently published papers where researchers do show that the same attack we showed here can be also done on modern GPUs. So do not let the targets fool you. We can do the attack on also much more complex systems. So for you who maybe do not know much about side channel and implementation attacks are those attacks that aim at the weakness of the algorithm, that do not aim at the weakness of the algorithm, but at the weakness of the implementation. And side channels are very famous type of the attack. They are passive, they are non-invasive, and actually they represent one of the most powerful categories of attacks on crypto devices. So this is commonly where most people will see side channel attacks, but that's not necessarily true. Wherever you have some kind of secret you want to obtain, you can use side channel information. You do not necessarily need to make that secret a secret key. Reverse engineering is a perfect example for side channel attacks. What kind of techniques do we commonly use in side channel analysis to make the attack? Well, there are multiple techniques. One simplest one will be called simple analysis, where, like the name says, it's simple. Why? Because you take one or a few measurements and you try some kind of visual inspection. The more complicated one is called differential analysis. So common example is differential power analysis, DPA, or for us here, it will be DMA, because we will use electromagnetic radiation as the source of the side channel leakage. How does it work? It works in a relatively simple way. You obtain a lot of measurements, so it uses statistics, and you recover some kind of secret information. So here we can see a sketch of, let's say, differential analysis. We have some input. On one side, we have real measurements with the real key or real information. On the other side, we have the model. We have the hypothetical output. We compare the hypothetical output with the real output. We do some kind of statistical analysis. We repeat this in a loop for all possible key hypotheses. And the one that looks the best, we say is the correct one. So this is the common setup we would see for attacking, for instance, AES with side channel attacks. For attacking, for instance, our neural networks, when we will be talking later about getting the weights from every possible neuron, just we will replace this word key with the word weight. So instead of doing key hypothesis, we will do all possible weight hypotheses. About the setup, you can see on the left figure, it is the target that we decapsulated. Why did we decapsulate? Well, because that improves the signal to noise ratio, but of course the attack works even without it. You will just need more measurements. And on the right side, you see the probe, the longer probe to obtain the measurements. In the full setup, it looks something like this. So we have the target, we have the probe doing measurements, and oscilloscope gathering the measurements. Okay, so now I said, well, this is the setup, but the question is, okay, but what exactly do we measure? So since we are attacking microcontrollers, the exploited leakage model will be the Hemingway leakage model. This is the commonly used in practice leakage model for targets like that. So a microcontroller will load sensitive data to a data bus, and it will perform some kind of instruction. What do? We have the training phase conducted offline, and then our train network implemented in C language and compiled on the microcontroller. What kind of behavior do we expect in this leakage model? Well, we expect the more ones in a byte value, the higher will be the leakage consumption. So you can think of, if I have a byte with only one and 7 zeros, it will be less pronounced on the oscilloscope wave than if I have a byte with 7 ones and 1 zero. So when we do the attack itself, when we say, well, now we want to recover our network architecture, but also our neural network parameters, the weights, what is it exactly that we want to recover? Well, we want to recover information about the layers. So how many layers do we have? Where are the boundaries between layers? Information about neurons. How many neurons do we have? Where are they? In what layer? Information about activation functions. Information about the weights. So first, I will show you every part separately. So how do we do attack on each of those? And then I will show you how the full framework looks like. And then you will see some practical results. So what is activation function? start with activation function because this is actually the easiest place to do the attack. So it's just a function defining the output of a node, input or set of inputs. So we have our weights multiplied by input, we add some bias, we do some summation, let's say, and then we do nonlinear activation function. What are the commonly used activation functions? Something like sigmoid, tan h, softmax, rel. Here I show you the equations, the expressions for those 4 activation functions. Immediately from here, you can notice one important thing. If I tell you we are using timing to attack this, you can see, okay, these 4 activation functions have actually very different expressions. As such, you could expect that the time needed for each of those activation functions will be relatively different. So let's see how it looks like. Well, this is something that we can directly observe on EM trace, and we will measure the timing of the activation function computation. So here you can see the mean, max, and mean computation time in nanoseconds. And these are just numbers, so maybe not as nice as the graph. So you can see here that the patterns look radically different. Also, the timing delay, the values on the y-axis are radically different. So for instance, ReLU goes to 6,000 or so, while sigmoid goes to 2.2 times to the power 5. So the level is radically different. So it immediately somehow becomes clear, okay, there shouldn't be a lot of problems in differentiating many activation functions. Let's talk about the other part, the part that intuitively sounds much more difficult. How would we recover the weights? Well, to recover the weights, I already gave you a hint before when I was showing you the diagram of DPA. The change that we do from that diagram, there I said we use some kind of statistical test. Now I'm saying, well, we will use correlation power analysis, and because we will use Pearson correlation as the statistical test. So what do we target? We target the multiplication of operation M. That operation is equal input times the weight. Remember from our model, we said we know the input, and now we need to guess the weight. It is very similar like you would do attack on crypto, where you know your plain text and you need to guess the key. So if we use the Hemingway leakage model, we will correlate the activity of the predicted output for all hypotheses of the weight. And then based on Pearson correlation, we will see that hopefully the correct weight will have higher correlation and it will stand out among all other wrong guesses. Of course, given enough measurements, the same as when you do the side channel attack on crypto, the more measurements you have, the better results you can get. The same goes here. The more operations or inference operations neural network does, the better for you. Before showing the results, let's just analyze how the compiler will handle floating point operations. Well, it will conform to the IEEE standard 754, so compatible representation. Since the device is 8-bit microcontroller, it will follow 32-bit pattern, and it will store things in 4 registers. So it will be 1 sign bit, 8 biased exponent bits, and 23 mantissa bits. So this is just for you to know, because we will be attacking every bit every byte separately, so that you know what we are actually getting from that byte. We target the multiplication, and we will assume different possibilities for weight values. So we will perform multiplication, estimate IEEE 754 binary representation of the output, and then recover 23 mantissa of the weight. And then, of course, sign exponent we will do separately. This is how it looks like. Left figure is first byte, right figure is the second byte. Of course, the same goes for the third and fourth byte. So the point here is this: when we tried the correct key, the correct weight, you could see that the correlation value was higher than for the wrong weight. And what we can also see, number of traces behaves rather stable. So even with a small number of traces, we have decent differentiation. But already for the second byte recovery, you can see here that if we use very small number of traces, the difference is not good. So actually, we want to go for, let's say, 1,000 measurements or so to really be able to differentiate between the wrong guesses and the correct one. So with this, hopefully, I managed to convince you that we can recover the weights, and how precisely you recover the weight depends only on the fact how many weight hypotheses you want to test. The more weight hypotheses you want to test, the more experiments, of course, need to have. Now let's talk about how do we reverse engineer the number of neurons, the number of layers. Well, we will use very simple technique there. So the one I mentioned at the beginning, SPA, or here again, SMA. And this is visual inspection of one measure. So here I show you three graphs. First one says one hidden layer with 6 neurons. And I think I can immediately convince you that this is clear. So if you check, we can really see 6 times repeating patterns. And that's why we say it's 6 neurons. For the second graph, I think convincing is a little bit more difficult because we can recognize patterns. See here, 1 pattern, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 in total. So I see 11 patterns, no problems there. But the question you should ask is, okay, but how do you know that the line, the red line comes here? How do you know that it is 2 layers with 6 and 5 neurons and not a single layer with 11 neurons, or three layers where 5, 5, 2 or 5, 5, 1, sorry, or any combination? The same somehow goes for the third figure. So while it's very clear that we can recognize neuron activities, it is less clear how can we recognize the boundaries between layers. And how do we do that? Well, we will repeat the same technique we used for recovering the weight. We will use, let's say, information in the sense of CPA or CMA. So we need to ask a question. If we want to recover the number of layers, and where are those layers? If we attack a single neuron, if that neuron belongs to one layer or to the next layer. And then we will do the weight recovery using 2 sets of data. So how do we start? Well, devices are sequential, so it's easy. We will start with the hidden layer, of course, because there is nothing before that. And then we will assume our input as some length n0, where we have input represented of the same size. And for every and any targeted neuron in the hidden layer, we will perform the weight recovery on different hypotheses. Our first hypothesis will be, well, the neuron is in the first hidden layer. And we will perform weight recovery individually using xi for all possible layers. Our second hypothesis will say, no, the neuron yn is in the next hidden layer. For this discussion, so that would be second hidden layer. We would again perform weight recovery. And then we would record for each hypothesis the maximum correlation value and compare. And since the correlation depends on both inputs to the multiplication operation, the incorrect hypothesis will result in a lower correlation. So it's very simple. We go neuron 1 and we ask, is it layer 1 or layer 2? The answer, it's layer 1. Okay, then we go for the next neuron and we ask, is it layer 1 or layer 2? Again, for instance, we get answer, it's layer 1. We go for neuron 3. Is it layer 1 or layer 2? Now we get answer, no, it is layer 2. We draw a line. We start again with new question, but now we ask question, is it layer 2 or layer 3? And we continue in that same way all the way to the end. So you can actually see that getting the boundary between layers is actually not so difficult. How would we then recover the full network layout? Because now I said we do this for this, we do that for that, but how do we combine? Well, we need to recover the neural network layer by layer. And for layer, for instance, we will do weight for each neuron one at a time. And then we will need to determine the output of the sum of the multiplication. So the number of neurons in the layer must be known. And then using the same set of traces, we will do the timing pattern to get the activation functions. And we will repeat this for every layer. So it's something like this. We start with the acquisition. We do our hypothesis to get the weights. After that, we get the neuron layers. After that, we get the activation functions. And we repeat this for every layer, every neuron, of course. And finally, we reconstruct the network. Let me show you now how does it look like when we are really trying to reconstruct the network. So this will be MLP architecture and ARM Cortex M3. So you can see here the patterns. And already you can see a bit less difference between sigmoid and tan8, less difference from the shape perspective. But if you look at the timing delay, so the magnitude of delay is rather different. So it's still relatively easy to understand what is one function versus what is the other. How does it look like? Patterns for timing, multiplication, activation function. So patterns, you can still see patterns, but are more difficult to recognize. Amplitudes are smaller. Correlation comparison between correct, incorrect values are less pronounced. So see here with this target already, I'm saying, well, we need 2,000 measurements, 2,000 traces to differentiate. Number of neurons, of course, you can see still very nicely patterned, but you need more experiments, and more experiments. Of course, this being said, this is still very small neural network and a very much unrealistic neural network, but it is nice simply to show you how it looks like. Because if I now show you a neural network with 200 neurons, well, it will be a lot of patterns for us to recognize just by looking. That being said, this does not mean it doesn't work. So we did experiments with more serious neural networks, but still multi-layer perceptrons. And for instance, we did experiments with two data sets. One, MNIST, well-known basically to anyone doing machine learning, and the other data set being DPAV4. This is, let's say, a common data set in side channel analysis. So what did we do? Well, we built a good performing neural network. So of course we wanted something that performs good, because if you would just take something random, then you would say, well, even if your reverse engineering is not good, you still end up with a random neural network, so they should behave similar. So we wanted to build a good neural network, and that neural network had accuracy of 60.9%. Network is 3 layers, hidden layers, where every layer has 50 neurons. And then what did we do? We did the reverse engineering attack, and the accuracy of what we reverse engineered had the accuracy of 60.87%. So you can see the small difference. Why get that difference? Why is it happening? Well, it happens for several reasons. First, if you are very wrong somewhere in the beginning, the error can propagate. And second, we never aim to be completely precise for every weight. Remember, we said the more precise the weights, the more weight hypothesis you need to do. So for instance, if we limit our attention to 2-3 decimal places, that will give us reasonable number of weights to go over. But of course, if there are many weights that are different on position 3, 4, 5, well, maybe the cumulative effect of those changes can give you also a bit different classification results. This is why we see a difference, but a small difference. For the MNIST data set, we basically used one of the neural networks recommended at Kaggle webpage, and the performance with that neural network was 98.16. And of course, this is not amazingly good performance, so there are more powerful neural networks, but we did not aim to find the most powerful neural network anyway. And then once we do the reverse engineering, our accuracy, the reverse engineering procedure was 98.15%. So you can see only second decimal place difference. And even more, I can tell you that the average weight error was converging to 0.0025. So for every neuron, the weight was difference, overall differences, so performance differences were basically nothing. But if you would really do the analysis of weights, you would see differences only third decimal places and later. So with this, I hope I convinced you we can do the attack with multi-layer perceptron, but I could also say, yeah, but this is a multi-layer perceptron. While it's good, it's powerful, all fine, but let's be honest, this is not state of the art. What about something like convolutional neural networks? And for convolutional neural networks, it still works. So here I will just briefly explain. Again, we used Cortex M3, and now we aimed for CNN architecture. We changed a dataset to Cycle-10 dataset simply to show that the overall methodology of reverse engineering does not depend on the datasets. And we choose as target application operation from the input with the weight. It's the same as we did for MLP. What differs from previous experiments, the operations on real values are here performed using fixed point arithmetics. So that means the numbers are stored using 8-bit data type, so int 8. And the resulting multiplication is stored in temporary int variable. So as one of the examples attacking Cypher-10, we had a relatively okay architecture for a data set of that difficulty. So convolution layer, pooling layer, fully connected layer. The original accuracy of CNN was 78.47%, and the accuracy of the recovered CNN was 78.11%. So we can see here it still works, but the differences are a little bit bigger because there is also, let's say, more noise in the experiments. So what we see here is correlation for the correct weight versus the wrong weight. And you can see that if you use a small number of measurements, you actually do not see much difference. So already if we would take, 50,000 traces, and remember before we were talking about 2,000, 5,000, you can see quite nice differentiation. Even for some bytes, if we do int 8, if we take something like 10,000 measurements, but if we do int variable, then you need something like 100,000 traces or more. So the attack works. The difference between previous attack and this attack is that you need more measurements. And the same kind of conclusion goes actually also to more difficult targets. So now if someone would say, well, I don't want to use ARM Cortex M3, I want to use something more difficult. Yes, we can still follow the same principles. If it's sequential, if it's in parallel, yes, you can still do the attack. It's the same like someone would say, well, can we do attack on AES, for instance, in hardware, where there are multiple rounds at the same clock cycle. So we are kind of using the same concepts to attack neural networks. With that, this is somehow the general procedure, how you can recover the neural network architecture, but also network model, so parameters. Before going for the second part, I will immediately just briefly tell you what are the challenges now, because I could say, okay, it works. What are the challenges? Well, first, you need to have a proper threat model where this kind of attack does make sense. Of course, if you're running something in a safe environment, when you're assuming that the attacker cannot approach, well, the measurements are difficult. Then you need to consider something along the lines of doing the remote attacks, which is, again, possible, but more difficult. Second is going for bigger and bigger architecture. We did that. And like I said, the only difference that we really observe is that we need more and more measurements, which means also that your attack will also take more time because you will need to measure more traces to get decent signal. Finally, going back to one of the first slides, I said there are no countermeasures. So what is it that we foresee that can be done there? Well, one easy option what could be done is, luckily there are some decent countermeasures that we know from cryptography, from how to protect cryptographic implementations that could be used here. For instance, you could shuffle the ordering of operations in specific neurons. If you do it just in a layer, you will not get a different output, this different solution, but yet the attack will be more difficult. There are many suggestions what and how to protect the neural networks against side channel attacks. Some are more conventional, so following the normal techniques, are very unconventional. So recently there is a paper on ePrint where they recommend actually to switch to different types of arithmetics, because in that type of arithmetics it can be easier to mask, and so on and so on. Next, I will talk how to recover the input of networks. So up to now, we knew the input and we tried to get the neural network model. Now, let's say we managed to do our attack. We now know our model. Model is in a device. Model does not change until someone makes a change to the model, uploads a new model. But new inputs in the inference phase are constantly coming. So how do we get the input for, how do we guess the input? Well, like I said, our assumption is we need to know the architecture, we need to know the weights, so the model, and we will do side channel attack like before. What do we need to do, where we need to put our attention is the first layer. Why the first layer? Because first layer processes the input. So this is where the attack makes most sense. And after first layer, the information propagates to all the other layers, but that is already more tricky to use. So now we switch. Before we said multiplication is known input multiplied by unknown weight. Now we say multiplication is equal to unknown input but known weights. Unfortunately, this small change makes a big change for the attack. Why? Because the attack now needs to work with a single trace, single measure. Why? Because your input, you have one input and you need to guess that input. Then you get the second input, you need to guess that input. But all the input is, if it doesn't work for one, already the second input, you cannot combine the information about two inputs. At the same time, weights are multiple, but they do not change. So everything happens from the perspective of the attack like before. So the training phase is offline, the model is in C language implemented, compiled on the microcontroller, and let's see how do we do it. So like I said, we do multiplication input times weight, but now input is secret. Since X changes from every measurement, we need to succeed in a single measurement. But we know how to do that. It is somehow similar situation to public key crypto, where you use ephemeral keys. Your key is used once, and then new encryption, it's a different key. So how do we succeed there with a single trace? Well, with something like horizontal attack. So how is it working? Well, for crypto, you basically try to cut your traces into 0-1 bits, and then you do pattern matching. How do we do it here? We'll take the weights in the first hidden layer. They are all multiplied with the same input X, one after the other. So there are M multiplications corresponding to M different weights, M different neurons, and remember, you know it. And then we can cut our single measurement, single input trace processing into M smaller traces, which will mean every part will correspond to one multiplication with a known associated weight. And then next, the value of the input will be statistically inferred by applying standard CPA as explained before. So what do? We basically do something like this. We have our input multiplied with weights. We cut it in many pieces. We put one piece below another one, and we kind of do pattern matching, and we recognize, okay, the input should be this, the input should be that. How does it work? Well, it works very nicely. So for instance, for AtMega, I show you here attack on the first byte. And we can see that if our first layer has 20 neurons or more, you can actually already get very decent approximation of what is correct, what is wrong from the perspective of correlation. As such, we found somewhere 70 multiplications are enough to recover the byte, the input, up to desired precision of 2 decimal digits. So we said, well, let's say we input up to 2 decimal places is enough, and with 70 multiplications, we are fine.
Just to let you know, 5 minutes.
Yes, no problem. And this result on a more difficult target, you can see here we need more neurons, but still very much doable for realistic architectures. And finally, just to show you example how it works. So you can see here, top row are the original images, bottom row are the recovered images. So the input that we guessed with our technique, and you can try to find the differences, but you cannot do that by just using the eyes, because indeed the differences are happening only after the second decimal place. With that being said, thank you very much for your attention. And if you have any questions, I will be very happy at least try to answer those questions. There are some questions in chat. Hossein has 2 questions. You mentioned that multilayer perceptron is the worst case scenario for such an analysis compared to other architectures, such as CNN having different intermediate layers, such as pooling, fully connected. I see this the same as when you apply intermediate layers, such as batch normalization, dropout, different activation layers in MLP. I was wondering what makes MLP more challenging than CNN in this context. Yes, actually, this is a good point. It was more from the perspective when we were starting with the experiments. We said, let's say every layer in a multi-layer perceptron will have the same activation function. And let's say we will assume the architecture where every layer will have the same number of neurons. And as such, intuitively, it sounded to us that differentiating then between layers or recognizing what is happening when will be more difficult, because everything will look really the same. For CNNs, for those different layers, those radically different operations, what is happening with convolutional layers, so where you have multiplications with the kernel for the number of channels, and combining with also things that have quite unique signature, like batch normalizations, or going to pooling layers that, again, very much different side channel leakage information. We said, well, there it could be more difficult to guess what is happening within the layer, but it should be more easily to recognize the repeating patterns, so differentiation between layers. So this is what makes MLP more challenging. The repeating of many things is making, for instance, a little bit more difficult to notice where is the boundary between the layers. Regarding retrieving weights from the model, how does your approach scale? Can it be used to retrieve weights from huge DNN models like GPT-3 transformer with 175 billion parameters? This is very big. I would say, realistically, the approach scales linearly with the size of the architecture, but I think this would be very difficult architecture to attack. There are 2 reasons for that. First, how would you fit all those in your oscilloscope, one measurement? So you would actually need to cut one trace into multiple traces and then combine it together. And for something like that is run on a serious hardware, you would also have very serious noise. So you would probably need a lot of measurements to obtain. So my guess, you would have bottlenecks from simply the acquisition perspective, but the attack should work. That being said, I would honestly not recommend this kind of technique for something so huge. There are extensions that we are working on that we actually do see that we can do a bit smarter attack and attack only specific parts and obtain good performance. That being said, I also need to mention that when we did the experiment, we actually went for the setup of more IoT devices, so devices that are relatively cheap all over. Huge models like this would also need to be implemented in a very serious hardware. So I don't really do GPT architecture, so I never really tried. But my guess for it, you would need a GPU, for instance, with a very serious GPU with a lot of RAM. Already, that device itself would make it very difficult to do the experiments because the noise from the whole GPU would be significant. And then you would need to obtain a lot of measurements. So there is a paper from this year where they attack GPU, and they need, if I'm not mistaken, the number of traces there counts in millions of traces. So my answer would be, well, if you have a decent setup to efficiently measure millions of traces, then the side channel perspective would not be such a huge bottleneck, because in realistic cryptographic implementations, you often also do attacks on millions and millions and millions of traces. So from a side channel perspective, I believe it's fine.
Okay, thank you very much. Is there any further question on this?
Stop sharing.
This is, of course, very short before lunch break, and I'm sure that some people are very hungry, running to their lunch. So, but as already mentioned, if you have any question, you can post it on the chat. We will redirect it to Stjepan, and whenever he has time, he will answer us, and he get back to you, or he answers you directly.
Yes, indeed. There is also my mail was on the last slide. So my first name @computer.org. If you have any questions, do ask. And yeah, since now it's lunch, a nice meal to everyone.
Asking question is free of charge, I assume, Stjepan. Yeah, you don't charge.
Of course.
So because Huawei is a good friend of us, we don't. That's okay. Anyway, so thanks a lot, Stjepan, for your time.